So, in very short, happy to see you back, Gabriel. He's one of the guys who not just talk about IPv6 stuff, but actually do it. And happy to see him back, as I know there's always a highly practical stuff.
Thanks for the introduction, Enno, and first of all, congrats to the 10th anniversary. So it's a pleasure to be invited again, and I'm really happy to be here. Okay, welcome all. As the title suggests, it's about IoT. Oh, lucky me. No, it's okay, I think it's just should be prepared better. No, it's good. Okay, sorry for this. So basically, we were interesting about how a gateway behaves in the IoT world, because we believe that although IoT means devices talking to other devices, this could be often in a, let's say, direct manner. We believe that often there will still be some, as we say, centralized communication patterns over a gateway to some other network, over the internet most probably. And this was the motivation for this talk, to evaluate how such a gateway can scope with IoT chattering, as we can call it. Okay. So before we start, basically a few words about myself. I'm working at AWK, mainly as a project manager, and I think it's not a secret, I'm working mainly of my time since years now for one of our customers, which is Sunrise, second largest internet service provider in Switzerland. And there I'm doing network projects in the fixed net area. Besides that, I'm also responsible for the AWK network in the main and the branch office locations, having 2 kids and living near Zurich in winter too. Okay, so motivation again, as introduced. Internet of Things, a lot of devices communicating to each other, most often in a distributed manner, but also often the need of having the need for having a connectivity to the internet. For me, it's because people often talk about Internet of Things, but just to define it in 1 or 2 keywords, for me this is related to machine-to-machine communication. And as already introduced, the internet is often used as some sort of transport networks. I listed a few examples here, just for the sake of completeness. And by the way, I'm not sure about the third bullet. I tried to find out this morning, but I didn't manage to. So I'm not sure about the Amazon button, if it's IPv6 enabled, so maybe one of you knows. So it might be not legitimate bullet. Okay. Yeah, and for the, I will soon come to the test setup. Within the test setup, we were focusing on address assignment, DNS, and neighbor cache. All this on this with respect to resource consumption on this centralized gateway, as we will soon see. Okay, coming to the test setup. So this is the test setup. It seems to be quite easy. In fact, it is. With this device, we initiated most of the test traffic towards the test device. So the test device is this Juniper firewall, SAX210 HE2. So HE2 is specifying in more detail the hardware configuration, which is in this case 2 gigabit of RAM. There were older configurations with only 1 gigabyte of RAM. On the left-hand side, you can see, as we call host B. This is, I could have called it anything, but in the following slide, it's called host B, so that you have a reference to this device. You can see the corresponding network configuration. And on the top, you can also see the management network, which we utilized to control all 3 systems, that we did not interfere with or compete with IPv6 traffic, especially under load situations. as it was appreciated last year, also this year I have printed out this sheet so that you can keep this in mind for the remaining of this presentation.
This is our professional speaker. That is the past in contrast to.
Well, there's still space to improve. Do this in advance to the talk. Kannst du ein bisschen in die Mitte ziehen, dann, Ali? Thanks. So. Any questions to the test setup? I think it's understandable. Let's call it like this. A bit more specifics on this firewall, which is required to understand my follow-up explanations. So this model is considered also considering its size as a branch firewall. It does not have dedicated hardware for control and data plane, but it's only dedicated cores. So it's one processor with multiple cores, and in this case it's a dual-core processor, and which has two CPUs. One is assigned to the control plane, and one is assigned to the data plane. The same applies to the memory. We have 2 GB overall, and roughly 1 GB is assigned to the control plane and 1 for the data plane. On the right-hand side, you can see also the schematic of this, I would say the architecture of this board of the firewall. And for those of you which are more interested in details, so what we utilized or what we looked at when we did all these measurements was this basically these two show commands. Of course, when I then in the course of the testing recorded such values, I did not do this by issuing the show command several times, but instead I gathered this data via SNMP. Every second I sent an SNMP GET request and stored the data in a CSV file, which I then later on used to generate all the graphs which are going to be shown. Again, some other picture again. So I'm not sure what about your knowledge about this. So I'm quite familiar with this concept because we also run these firewalls in our company's network. For those which are not that familiar with, Juniper has a very good, I would say, design that they really separate task and assign it either to the routing engine or to the packet forward engine in order to assure fast packet forwarding and for all this management related activities, daemons, whatever. So also a DHCP daemon, for example, would reside within the routing engine and not in the packet forwarding engine. So that all these daemons management wise and also the routing updates, this is handled by some other entity in order to not conflict with packet forwarding activities. Okay, so with respect to the testing, we subdivided it into two parts. Part one would be, I called it host to host, and in part two I tried to simulate as much as possible communication of many hosts to many hosts. So let's start with the first part of the testing. These are the three test cases. So we have a ping flooding test, we have DNS testing, and also DHCP v6 testing. The ping test I executed to get a feeling in terms of how many sessions the firewall can scope with. DNS testing, I would say, is more or less obvious. If you're in a network and you want to connect to the outside, this is, I would say, 99.9% of the cases you need DNS to resolve the IP address. And DHCP v6 testing was to see if this could be an alternative performance-wise, not about all the specifics which Enno mentioned in his former talk, but more to see also again load-wise what the firewall can offer us here. Okay, so let's start with ping testing. At the very beginning, I sent simple ping packets as you used to do it. So then usually the ping application sends one ping every second, and of course awaits the corresponding echo reply packet. This results in an average round trip time of 2.2 milliseconds. And of course, if you're doing the math and divided 1 second by this number of milliseconds, you should get the possible number of pings per second. And then in the Unix domain, you have you can use a ping application with a -f option, which tells the application to send an echo request packet, and as soon as this echo reply packet has arrived or received, it will send the next echo request packet. For this, you have to have root privileges, because it can have significant impact on the load of the device. And so with one ping session, we then achieved 453 pings per second to the firewall. And if we compare this with SNMP data we gathered, just also to have some cross-check, it was more or less the same. So now, before I show the next slide, which will show the load, what do you expect in terms of load? If you recall the other picture, which I did not print out, with the distinction between the routing and the packet forwarding engine. So where would you expect the load now? Okay, so no guess?
Very small.
No, it's quite. Remember, it's a branch firewall. It's not. Okay. No, I was asking more about which, because we have two CPU cores, right? If you remember, we have one assigned to the routing engine and one to the packet forwarding engine. So this is a service processing unit graph. And as you can see, the higher load is on the routing engine, because what we do we ping the firewall, and this packet is sent from the packet forward engine. The packet forward engine cannot handle it, or well, it sees that this packet is not destinated to some other element in the network, but it is destinated for itself, and itself means it has to bring it to the routing engine, and the routing engine then responds to this packet. Okay, and let's say the utilization of this packet forwarding engine is much lower, with roughly 30%. Okay, so what we also did, of course, some question, yeah? As I said, with SNMP, I measured the data with SNMP. Okay. Next test was that we did not ping the firewall, but we pinged this famous host B over the firewall. And with one ping session, we achieved 1,242 pings per second. Again, compared to the data measured by SNMP, which is 1,243, so quite accurate and in line with what we saw on the command prompt. Again, my question, where we will now have the load. So load.
Should be the other way from packet forward.
Exactly. Now it's on the packet forwarding engine or on this SP unit, because the packet is not designated for the firewall, but for a host which is connected to the firewall. So the only, let's say, duty of the firewall is to, of course, first of all, to see if the packet is allowed, a legitimate one. It is. I configured the security policies accordingly. And then it has simply to forward the packet, and this is then to host B, and therefore we only have the high load on the packet forwarding engine, or SPU, as we call it in the picture. Okay, of course I wanted to see, you can now see the overall capacity we achieved so far was limited because of the round trip time, because we have a certain round trip time, and this round trip time defines the maximum number of ping packets I can send per second with one ping session. So in the next test or sub-test case, we started 5 ping sessions in parallel. Now first again to the firewall itself. And you might remember the value we saw with 1 ping session, which was roughly 500 ping sessions. And now we see we could achieve 985 ping sessions. So here you can see that the firewall reached its maximum capacity, because if we would have if we would multiply the 500 seconds we saw per ping session, we would end up with 2.5 thousand sessions, which we cannot achieve. And also you can see now that the round trip times become higher, right? So it's instead of 2 point something seconds, it's 5 point something milliseconds. And this you can also see at the graphs that let's say the control, the routing engine, which is the control plane, it now gets saturated, right? So at a certain point in time, CPU utilization reaches 100% and stays at 100% as long as we keep pinging the device.
Why does it take so long to get to 100%? Is that averaging in the measurement?
I don't know. To be honest, I asked the same question myself. My assumption is that for whatever reason, it keeps still track of something of the old ICMP session.
Because it only goes to 100% after exactly 300 seconds. And I think the CPU value is a 5-minute average.
This is good point. It would be a bit problematic, because then my results. I'm a bit. Let's talk after the talk again, because I didn't think it. Or I took the wrong value when I displayed or created the graph. Is it the same here? No, here we had it after. Here we came saturated after 180 seconds. So keep your assumption in mind, and we will check the next graphs as well. Okay. Okay. Again, the same testing. This is 5 pings in parallel to the host B again. And as you can see here, it works out better that we can achieve 2,600 packets, ping packets per second. And again, my question, but I guess you should got it right. So now, of course, we have the contrast that the routing engine is not heavily utilized, because it basically does not have to do anything. And but what becomes saturated now is a packet forwarding engine, right? Which makes some sense. I think, yeah. So to really see that it makes a difference, I also connected the 2 laptops directly with each other and executed this test, and you can see we can achieve even more pings per second, which is, again, if you look at also about it's not only because of the let's say capacity of the firewall, but also about round trip times, right? They're now, of course, shorter again. I think this, yeah. So to summarize this, for me at least, it was like expected. If the traffic was targeted towards the routing engine, we saw corresponding high load on the routing engine, and if the traffic was only passing the firewall, we saw high data plane packet forwarding engine load. This is the SPO node. Mainly, we saw very good, let's say, SNMP accuracy with respect to the measured values. There was one where it was not matching 100%, and here my assumption is, in case the SPU is highly loaded, then it lags, or it cannot on time report the data to the routing engine, and of course then in consequence the routing engine itself cannot report the proper values by the SNMP daemon to the querying devices. And also, when you look at the spec sheet of Juniper itself, remember we saw roughly 2,600 sessions, so it even overachieved a bit the connections, or connections per second, because ICMP, right, it's you send an echo request, you receive the corresponding echo response, and then the session is finished, right? Questions so far? I'll then go to the next test, which is the DNS testing, also, again, performance-related testing. I found a tool which is called DNSPerf from some, I think this company also offers the DNS server applications. So it's they more or less published the tool they use themselves for that application testing. It's quite easy to use. You just define, as you can see on the lower right side, the content of some input file, which just states the DNS entries you would like to query, and in our case, of course, it's a quad A record we would like to query for. Then you specify this file as input, and you define with -L is the maximum runtime, which would be 600 seconds, and -C is the number of clients, which is simulated by 2000 in this case. I then configured the SRX accordingly as a DNS proxy and started this test. And what is highlighted in bold is this 162 queries, which were successfully answered by the firewall. Which for a branch firewall, I would say is quite good. Yeah. Again, the corresponding load, and again, since this is some daemon which runs within the routing engine, the corresponding CP load is quite heavily utilized. And since 162 packets, basically, UDP packets, or plus 162 packets in response to this, this causes obviously only very little load on the packet forwarding engine. Yeah, this is the slope. I just to cross-check again the value reported by the application with the SNMP data I gathered. So, and here you can see a slope of 162 as well, which indicates that at least the firewall reported the same quantities of DNS queries received and responses sent. And you can also very nicely see that the number of DNS queries received and DNS responses sent is the same, because the two lines are overlapping exactly. So it's a good result. Who is aware about Juniper application level gateway? Yeah, you made positive or negative experience with this?
I know what it does and what it exists.
Right. Okay, that is at least good that you know that it is there, because I was not. You didn't. Okay, I can come later. So basically, the thing which is important here is application layer or level. So the firewall is doing something at application layer, which of course means the firewall has to look into the packet quite detailedly to analyze this and to make some assessment on it, right? And basically this feature is enabled by default. And now what I did, I disabled it. And I run the test again against the firewall, which had no big impact for 4 queries per second. But what is more interesting, this is the corresponding load graph, so same here. Did I delete? No, okay. So this is now that, as you can also see at the IP address, I now did not run the DNS performance testing against the firewall, but against the host B. I set up a DNS mask, very simple, just to act as a DNS server, or DNS proxy more or less, and run the test again. Now with this still DNS ARC enabled, and you can see I can achieve roughly 4,400 packets or queries per second with, again, the corresponding load graphs. But the interesting thing is, after I disabled this feature, I could reach factor 9 more throughput. So it really has some performance impact on the number of queries you are able to send. And as I said, this is also makes totally sense. If you disable this feature, the firewall will not look that closely into the DNS packets and can achieve much more throughput in this case. Again, the corresponding load graphs. By the way, what is I'm not sure if you noticed before, but what is really interesting that because I'm not only displaying the CPU load of both cores, but also the memory load of both memory used by the routing engine and memory used by the packet forwarding engine. And you might have observed it's quite it's not changing, so it's not increasing or decreasing. It's quite constant all the time, all the measurements. And here my assumption is that the firewall per default sets aside a lot of memory or allocates a lot of memory to be prepared and to ensure that memory is not exhausted. We see one example where it's different later on. But yeah, I think we also, yeah, exactly. We already coming to the conclusion here for the DNS related measurements. So, as I said before, I think it's fair result for when we use SRX as a DNS proxy, given its proposed or not proposed, its intended use in a branch office, and also the forwarding. So, in case SRX has to simply forward these packets, it's quite a good result that we could even transport 34,000 DNS requests per second to the host B. Also to this I skipped, pardon me. This is again the result if I connect the both laptops directly without a firewall in between. So you can see that the 34,000 packets we measured over the firewall is not limited due to the capacity of the host B laptop, but host B, if directly connected to the other measurement laptop, can achieve or can answer up to 50,000 queries per second, which is it's running Ubuntu and DNS mask, and I think it's quite a reasonable result to answer for 50,000 requests per second. Okay, what we really do not like is this DNS ARC feature, and when I did the testing and I disabled it by issuing the command, I remembered something, and then I looked back into my migration notes of 2016 when I migrated our firewalls, and I saw that this was exactly the feature which nearly ruined my migration attempt. And because they have this ARC feature is doing something very nasty, which they call DNS doctoring. And this is if you have a one-to-one IPv4 net configured, a static net configured on the firewall, it transparently, in every DNS request it sees for this IP address, it replaces a public firewall which comes from an external DNS server as a response and replaces this with the internal IP address. And you might say, well, this is a good thing, because if the clients in the trust network are connecting to this resource, they will not go over the firewall, but they will get the internal IP and connect to this directly. Fair, but in my company we have, let's say, a guest Wi-Fi, which is also used by all the employees for their mobile devices, and they sync the emails about this device, and of course then they will get an internal IP address they cannot connect to, because the guest Wi-Fi obviously only offers internet access and nothing more. And yeah, so fortunately there was a guy which had the same experience back in 2012, and he posted this in a post, and I could find it thanks to Google in the night and continue with my migration. Any questions with respect to DNS? Okay, DHCP v6. A very short recap. So about the DHCP v6 handshake. So after the client has received the route advertisement and the management flag, the management flag is set, he will start to send a solicited message to a well-known multicast address, and available DHCP servers listening on this multicast address will advertise themselves, like I'm here. And but only with the third message, with the DHCP request, the client is in fact requesting IP address, and in case the DHCP server can give him an address, he will send a reply with a DHCP ACK packet. Why I'm showing this to you? Because it took me some time to find a proper test tool which is dealing with this four-way handshake and with the states. So the test tool needs to send a solicitate and needs then to wait for the corresponding advertise from the firewall in order to send the corresponding request afterwards, so that the firewall has really the impression that it's a legitimate DHCP request, right? Fortunately, I found such a tool, which is perf DHCP, and also here you can, it's quite easy to invoke. You -X is for IPv6, -3, minus small r is you tell him what is the expected rate you would expect to see, how many requests can be answered by the DHCP server, and minus big R is the number of clients the tool should simulate. It gives very nice statistics once finished. So for the first two messages, it gives you detailed statistics, how many packets, so this would be the solicited packets, have been sent, and how many advertisements have then been received. As you can now see, this number is not equal, right? So even with a rate of 25, with expected 30 requests per second, the firewall seems cannot scope with this number of requests, and is not answering to every solicited message. For the advertise receive, of course the tool then sends a corresponding request, and here you can see that the number of requests and replies is matching. So at least the managed then for those advertised messages the firewall sent, the firewall itself was able to then also reply to the corresponding reply packets in the second stage. Again, the load graph, and which is again obvious. This is a DHCP daemon also runs on the routing engine correspondingly, or in consequence, the CPU load here gets quite exhausted. As I mentioned before, this is the only test case I could saw an increasing memory occupation, and also you can see this not on the packet forwarding engine, but on the routing engine. So the memory of the routing engine or the utilization has increased by roughly 7% here. Okay, and here also to cross-check with the SNMP data, or with the data the tool reported, again the SNMP data. The slope is, as we saw, so 26 requests per second could on average be confirmed. But you now see here that there's a deviation, so the lines are not all overlapping, but instead we can now see that the firewall tells you this by the statistics it reports via SNMP, so it tells us that it has dropped some DHCP messages or requests which arrived at the firewall. Now we utilized the firewall as a relay, so that I told the firewall to forward all DHCP requests to host B, and again, we see quite similar values, also in the same, let's say, capacity domain. So before we had something about 8,000 requests received and responses sent, and also the rate is with 25. It's quite close to the other value. At the very first, when I looked at the result, I was a bit confused because I thought, well, the host B is much more performant, right? But then you have to realize that the host which is requesting the DHCP, it sends this packet to a multicast address. And the firewall has to forward this multicast address to the routing engine because it looks like the packet is destined for the firewall because it lists to this multicast address. But then only the routing engine or the DHCP daemon in the routing engine can see, I'm just configured as a relay, so I have to forward this packet to host B. And this is since the processing, again, needs to take place at the routing engine for all packets arriving. It's some kind of reasonable that we get or achieve similar results, even if the firewall is only configured as a DHCP relay, right? And here we don't see this high increase in the memory, but this also makes sense for me because in this case the firewall only forwards requests but does not assign addresses and consequently does not have to keep track of these addresses by utilizing memory to store the information in the memory for this address, the lease time and all this do-ID. Of course, again, to see what is realistic, we connected the testing laptop and host B again directly, and compared to 25 requests or exchanges per second, we now have nearly 2,000 requests per second. Again, it was a DNS mask I used for this testing. So it was not, the bottleneck was obviously not the host B and its DHCP server. Okay, also here to show you this, I hope you can read it. So just the message flow, as I indicated at the very beginning. We have the solicited message, we have the corresponding advertise message, and then we have the request and the reply message for one client ID, and then you can see it's enumerated. So at the end it's 304, and then 305, and you could see this in the traces that it's simply increased the number of the client ID by 1 for the requests. Okay. Again, regarding the performance, I think it's fair. And what I did not show in detail, but what I saw when I looked at the DHCP details at the firewall, that there seems to be a limit. And I had very strange entries if I exceeded this limit by, which was about 5,000, not requests, but entries, I would say. But a branch firewall with 5,000 entries, so this is then obviously not the right device for such an environment. Yeah. Okay. Yeah, we saw this already, or I already explained this, that if we utilize the SRX as DHCP relay, we had the same performance. This was, as I indicated or explained, because the packets have to be treated by the routing engine, although the routing engine is not acting as a DHCP server. What could we do as well? So we could go for stateless auto-configuration and utilize the firewall only for DNS-related configuration, right? I configured this, and obviously the big advantage of such a configuration would be that we don't again have to keep track on the DHCP IP addresses. So we have also the DHCP server has no state information which has to keep track of, and you can see this now here that in case I effectively tested it. that in case the DHCP server on the firewall is only acting as for issuing DNS info, so for this other information, he is not storing any DHCP-v6 related information, which is a good thing. So at least you can be safe, or you can prevent memory exhaustion. Okay, now the second part, maybe because I used a very nice tool, I could quickly demonstrate this for you. Who of you knows ostinato? You will, I think you will like it. Time. Okay. Okay, so this is a quite nice tool. I will open a session I saved or configuration. Is it readable for you? I think I cannot enlarge it. Sorry for this. Oh, shit. Hab ich den jetzt gerade überschrieben? I think I just deleted the. So. I overwrote the Okay, so anyway, doesn't matter. So basically this tool you can utilize to generate traffic, and in this window it shows you all the interfaces, and you can define, let's say, here you can define, you can craft packets basically. So in this case I have configured an ICMP echo request packet, and you can define all this, all the, let's say, IP header, or not the whole packet header you can configure. And of course, if I now would just execute this, it would send an ICMP request packet. But since I have not configured any interface with the source IP address, the neighbor solicitation, the neighbor advertisement would not work, right? Because there is no IP configured anyway. So if the receiving host receives this ICMP request, it would not respond to it, or it would try to respond, but it could not. So this is why you can also define virtual IP addresses, which you just say can configure, and you can then also populate this. And now it created these entries, and now you can just run this. And it's also very nice that you have some record feature which you can enable. So now run the testing. We now send 1 ping per second to this existing destination, and now we stop and then you can open the pcap file directly here, and exactly so this I can forge it. Can you read it? So you can okay. This was a configuration which was not 100% properly done, because because it's now decreasing and not increasing. But you can see here the neighbor. You should exactly. Here you see the ping request sourced by 100, destinated for 10. You see the corresponding neighbor solicitation message from the recipient, because he now needs to know the MAC address. The simulated node is responding to this neighbor solicitation message with the neighbor advertisement message, and then we should also see the. Habe ich das? Ah, okay, nein, eigentlich nicht. Danke. So then but I'm still looking for the echo reply. That's only so I cannot say, but let's fix this quickly. Decrement, increment. So I should work now. Better. Okay, let's see. Yeah, okay. Now we don't see any longer, obviously, the neighbor solicitation, neighbor advertisement, because it's already in the neighbor cache of the target. But you now see the request and reply message, and you can also see, if you have a look, this is the target, and if I now look at the neighbor cache, you can see for the devices there, of course, there are some failed because we did it the wrong order, but for the device, no. Well, let's do it again. Sorry for this. Okay, so we flush the neighbor cache. We don't do the ping again. Let's do first the ripple. Okay. Okay, now it looks as expected. So full. Okay. So we send an HMP request, an ICMP request, sorry, ping request. We see the neighbor solicitation, neighbor advertisement. We see the ping, but we still don't see the reply. So sorry. So yeah. So we also see the reply. Then we see the the request for source by 101. We see the solicitation for 101. We see the advertisement for 101. And then we should also see the reply from the targeted host to 101. And now if we go to the host again and check the neighbor. Okay. Yeah, it still has the entries which of the device which failed, even so I flushed it. But you can see now for 105, 104, 103, 102. So we can see now the entries for the neighbors, which are simulated by the software. Questions to the software? Otherwise I would continue with the talk. Okay. Okay, so for this second part of the testing, we have defined 3 test cases by using the software I just demonstrated, Ostinetto. So in the first test case, we send a router solicitation message to the firewall. In the second case, it's neighbor solicitation messages to the firewall. And in the third one, we send ICMP echo requests, not to the firewall, but to the network on host B. And yeah, this I just demonstrated. What I did not show you so far is that you can start a second instance or a third instance on remote systems, and then you can, via a management network, you can connect to those remote systems of this ostinato software, and then you can also, for example, simulate virtual IP addresses on the destination network, as I did for this testing. Okay, so I think given the time, I will only go to this very roughly. So the ostinato software offers some, let's say, default packet types, but router solicitation was not one of those. So you had to, and you can, I had to define such a packet from scratch. And yeah, so this is the content of the package I set up and then sent to the firewall. It's a bit tricky because you have quite to have a very good understanding of the packet structure and packet creation. So for me it took 2 attempts. First one I did not specify the payload length correctly, and Wireshark even indicated this to me, and obviously because it looked strange, the firewall also did not respond to such a packet. So in the second attempt it worked, and so as I said, it was because I entered the wrong payload length. Okay, so my famous question, what do we expect for router solicitation messages sent to the firewall? So it's handled by the routing engine again, so we should see a high load on the routing engine, which we didn't. And I was a bit okay. I said, let's go with a higher frequency. So 200 per second. It increased a bit, but not that much, as I would expect. And also with 500 per second, it did not increase that much. So I took a closer look with Wireshark, and then it becomes quite obvious the behavior of the firewall. So it receives a router solicitation message, and it answers accordingly with a router advertisement message. But then for the upcoming router solicitation message, the firewall is not answering. Yeah, it seems to be some, exactly, it seems to be some, let's say, throttling in order to not exaggerate the resource usage on the firewall. And
Because the RFCs are very detailed on that.
oh, really?
To avoid flooding by basically, for instance, if you start up the whole stuff with the whole link, otherwise all the devices, the individual nodes, what code the router more or less so you're already spreading, and you're trying to, if you send an advertisement already, when you keep quiet, because the other ones will hear the advertisement even if they have not solicited it.
Okay, exactly. So because this was also my judgment, it's a valid approach because it's destinated to the answer of the firewall is destinated to the all nodes multicast address. So all the other nodes will receive the packet as well, and it does. It's a valid approach. Yeah, and this would also explain the routing engine, which is not that highly loaded with the traffic. Yeah.
Just check the timers in the RFC. It confirms exactly to the RFC.
Wow.
It says must not send an array more than every 3 seconds.
Yeah, this is quite accurate. Yeah. Okay. Good implementation then. Huh? Thanks for the checking. Okay, I have to hurry a bit given the time. Router solicitation. No, this is neighbor. So this is a type. I'm sorry. So this is basically now in this test case we send not the router solicitation but neighbor solicitation message to the firewall. And here it's a bit different, right? Because we are now not asking for a router but for a neighbor, and this has to be answered by the firewall for every request it receives. This has to be answered. And yeah, as I just explained. And okay, of course we had also to create this or craft this packet. And we also had to add the IP address we were looking for in the payload of the packet. And as we see, The load, the absolute load is not that high, is equal to the other picture, but you have to see the magnitude. We send much less packets per second here, and we have already a load of 35% of the routing engine now. And the same with 50 packets per second, it's even higher. I think this is, yeah.
Did you test the opportunity power as Rahmen against neighbor cache?
No, I did not test, no, sorry. But again, yeah, I know, yeah. Thanks. Given the fact that you see again these lines which are quite constantly, which reflect the memory usage. So I think they have done a quite good job to protect pretend memory exhaustion. Prevent, sorry. Yeah, and this is also what we assumed in advance, that given the fact that it has to answer each request, the load is higher. So then I come to the last test case, which is that, as I said already, we had two instances of this ostinato running, one on each laptop, and the laptop host B, he simply simulated IP addresses, because if I now send a ping packet from the right-hand laptop over the firewall designated to some IP address in the host B network, the firewall, it either has the neighbor in its cache already, and if not, it will issue a neighbor solicitation method to find out the MAC address of the target IP address. And depending if the firewall has to do it or not, we would see higher traffic on the routing engine as well. In this test case, since CPU load is not that high, so it's not that high, I had to assume that the entries already have been in the cache from former test runs. Here it also, because you can see the frequency I used, there is unfortunately a bug in this ostinato software, so if I used or run it with higher frequencies, more packets per second, it crashed. So it's and I was considering to compile it from source, but unfortunately I did not have the time to do so. And this becomes also a bit, you can also see this disadvantage if you simply ping such an IP address. You see the latency, it's quite high, given that they're on the same network, right? So I think you can. So obviously the ostinato has to listen for all packets, and if it receives a packet which is it should simulate an IP address, it has to respond to the neighbor solicitation message, it has to craft a ICMP ping response packet. So and this is given because basically if you ping localhost, it's I don't know, it's quite low, quite latency compared to these values. Okay, so time is done anyway. Okay. I know, 2-3 minutes, it's okay. Okay, so overall, considering the test device and the, let's say, capacity, I would say the performance we observed is quite reasonable. What you have to consider is that we had only very basic configuration on the device. So even on the network level, we did not have any dynamic routing, we did not have any IPsec, no syslog configured, and because this is also possible with such Juniper devices, you could have also some applications.
Test 1, 2, 3, Test. Ich glaube nicht, dass da was. Ah, jetzt ganz leise, ja. Mhm. Test 1, 2, 3. Ich glaube, das ist zu leise.
Das ist der falsche Kanal, I guess.
Audio-Test 1, 2, 3, Audio-Test.
Okay.
Audio-Test 1, 2, 3, Audio-Test. Audio-Test 1, 2, 3, 4, 5, Audio-Test. Sub-Network Dependent Convergence Protocol. Ah.
Okay. Okay, thanks. So. Looks like... okay, so and there's no application-specific software was running on the firewall, because you can have some antivirus application even be running on the firewall, which we did not. The simulation stuff, as you can saw, or you saw it in the second part, it was quite challenging to find tools, also tools which are able to do this state stuff, right? To respond to an SMP request or to simulate a neighbor solicitation, neighbor advertisement message, because there are a lot of tools, to the best of my knowledge, which can generate traffic one directional, right? They send a lot of traffic. It can have arbitrary content in this traffic, but to having this bidirectional traffic, this is quite challenging, especially in the, I would say, in the open source domain. I know that the test centers like Sparian, you can have this, but I did not have access to such a tool, and to rent it is a bit too expensive. Biggest advantage to myself, and I also hope that I gave you some input here. Again, a lot of IPv6 specific recap for my own, and to get some more insights in the Ubuntu networking, Ostinato, and also again Juniper SX. Also, I operate it in my company on a more or less daily basis. Yeah, this is a bit. Yeah, maybe 1 or 2 questions before we have to quit.
Any questions? I mean, we can take 1 or 2, even so long. I'm not in a position to judge on.
Okay.
Thank you very much.
Thanks.